Now, let us see how exactly the amylase assay is performed. This is just an example. So, in order to understand the methodology of measuring the enzyme activity, in this case, measuring the amylase activity, we need to understand few definitions that you might have learned during your theory. So let us repeat that. Let us see first what is the definition of enzyme activity. So enzyme activity, it is always measured in units. We call it as enzyme units. So these units indicate the rate of reaction catalyzed by that enzyme, and that is expressed in terms of micromoles of substrate transformed or micromoles of the product form per minute. That is the definition of enzyme activity. Now, according to international standards, one unit of enzyme activity for most of the enzymes is defined as the amount of enzyme causing transformation of 1 micromole of substrate to the product per minute at 25 degrees Celsius under optimal conditions of measurement, or the amount of enzyme responsible for the formation of 1 micromole of the product per minute at 25 degrees Celsius. This is how the definition of enzyme activity is generated. So the term activity, it refers to the total units of enzyme in the solution. There is another term called as specific activity or specific enzyme activity. Why it is called as specific? Because you have a solution, and in that solution there is presence of your enzyme, and along with that enzyme there may be presence of several other proteins. So in this case, considering that the nature of enzyme is proteinic, so in your given preparation mixture, as it is a mixture, it is a mixture of several things. Your enzyme, and along with your enzyme there may be presence of several other proteins. So in that given preparation of protein, specifically you want to measure the activity of your enzyme, that is determined by specific enzyme activity. That means in the whole preparation of protein, how much is the concentration of your enzyme in comparison to total protein content of that preparation. So therefore, the specific activity, it is the number of enzyme units per milligram of total protein. Therefore, obviously the formula will, this is the formula for specific enzyme activity, that is the number of enzyme units. It may be total number or it may be per ml divided by the concentration of protein in milligrams per ml. It may be concentration or total protein. Now, the protocol for amylase assay. For this, these are the following requirements. So the first step in amylase assay is preparation of standard graph of the product. Now what we consider the enzyme catalyzed reaction of amylase is starch is the substrate which is converted to glucose and maltose. So you can express your results in terms of the product formed, that is glucose or maltose. Therefore, we can consider either glucose or maltose as the final product, and we can express enzyme activity in terms of glucose form, micromoles of glucose form, that is product form, or micromoles of maltose form. So we need to prepare a standard graph of glucose or maltose. So in this practical, we'll be preparing standard graph of glucose. I'll explain you how to prepare standard graph of glucose. For this, the requirements are test tubes, DNSA reagent, that is dinitrosalicylic acid reagent, glucose solution, boiling water bath, and spectrophotometer at 540 nanometer. This is a colorimetric estimation, and in this case the reagent which is responsible for the development of color is dinitrosalicylic acid reagent. You might have learned about the principle of DNSA method. That DNSA method, it is useful for measuring the concentration of reducing sugars. So glucose is a reducing sugar, maltose is a reducing sugar. So in this case, we can use DNSA reagent for the determination of concentration of glucose, as it is a reducing sugar. So when this reducing sugar, it reduces DNSA reagent, it leads to development of a brown color complex, and which can be measured colorimetrically. Now this is the table for preparation of standard graph of glucose. So make 7 columns. The first column is the glucose concentration in millimoles. So we are going to prepare a standard graph in this range 1 to 10 millimoles, and at the end it is blank. So we have second column is stock glucose solution ml, that is the stock glucose solution is made up with a strength of 100 millimolars. Now first let us see what is the principle of this DNSA. So when alkaline solution of 3,5-dinitrosalicylic acid reacts with aldehyde groups on the reducing sugar, that is glucose, lactose or maltose, it is converted to 3-amino 5-nitrosalicylic acid, which gives orange color, which can be read at the wavelength of 540 nanometers using spectrophotometer. So there is production of orange color complex and not brown color complex. So it is orange color complex. That is the principle of DNSA, which I have repeated for your understanding. Then the next question arises, how to prepare this glucose stock solution. These are the dilutions of glucose that we have to prepare. And when we go on adding this DNSA to this glucose solution, according to the concentration of glucose, it is going to generate the color, the product or the solution of with different color intensity. So let us see how this 100 millimoles stock solution of glucose is prepared. So 1 molar is equal to 1000 millimolar, and we know that 1 molar, how do we prepare 1 molar solution? We dissolve 180 grams of glucose in 1 liter of water, that will give you a solution of glucose with strength of 1 molar, that is 1000 millimolar solution. Then in order to prepare 100 millimolar solution, what we can do is take 18 grams of glucose in 1 liter, dissolve it, that will result into 100 millimolar solution. Very simple. And this solution will use it for the making of solutions of strength 1 to 10 millimolar. How to do that? Now see, for the preparation of solution of 1 millimolar from 100 millimolar, what we can do is simply follow the formula of RT by G. R is required, T is total volume that you want to prepare, and G is the given concentration. Now required concentration is 1 millimolar. The total volume we want to prepare is 1 ml divided by G. Given is 100 millimolar. We have this 100 millimolar. So we want to prepare 1 millimolar from 100 millimolar. So RT by G, it will be 1 into 1 divided by 100 millimolar. So it will be 0.01 ml. So take 0.01 ml and the total volume is 1 ml, T is 1 ml. So 0.01 minus 1 ml is 0.99 ml. So 0.99 ml plus 0.01 ml, it is 1 ml. So put this value here, 0.01 ml, and 0.99 ml, put this value here. So the total volume is 1 ml. This is how you have to repeat it for this. So here required is 2, total is 1, given is 100, so it will be 0.02. And in order to make total volume of 1 ml, it will be distilled water, you have to add 0.98. This is how you can go on calculating on your own till 10 millimolars and remaining amount. So this will be the quantity of glucose solution 100 millimolars, and this will be the distilled water to make the volume to 1 ml. This is how you can feel column number 2 and column number 3. Then after mixing, okay, the last one is the blank. So these are the 10 tubes that you have to take, and the 11th tube will be labeled as blank. So what we have to add in blank is 1 ml of distilled water only, and later on we have to add 1 ml of DNSA solution in all the tubes, all 11 tubes. Now what is the use of blank? Because DNSA is a yellow colored reagent, and we are interested in the color which is generated after the reaction of glucose and DNSA only. So in order to eliminate the self color of DNSA, we must use this blank to adjust 100% transmission, or we can measure the optical density of blank, and then we can subtract this optical density from the optical density reading of sample. After addition of DNSA, boil the tubes. Keep all these tubes in boiling water bath for 10 minutes. So this is going to generate the color, and then make up the volume to 10 ml. That means this is 1 ml, this is 1 ml, and the remaining amount is 8 ml you have to add. So this will create the dilution of this sample. So add 8 ml of distilled water, and now after mixing, the tubes are ready for the reading at 540 nanometers in spectrophotometer. So for this, the blank used is this. Measure the optical density of all the tubes, and you will find that as the concentration increases, the optical density it also increases. So now you have two parameters: concentration of glucose in millimoles and optical density readings. So we can plot a standard graph now like this. So on the y-axis it is optical density at 540 nanometers. On the x-axis it is glucose concentration in millimoles. Now we have drawn a line. So as it follows the Beer and Lambert's law, as the concentration increases, the optical density it also increases, and we have to draw a best fit line. So this graph is generated in Excel, so you can see that R square value it indicates the accuracy of the data. So it is 0.979, that means it is approximately 98%. The linearity is 98%, so it is a good quality data. And this is the equation, that is y is equal to mx plus c. This you can use to convert optical density readings into glucose concentration. So if we draw this line through center, then this c will be 0, and the formula will be x equal to your reading of optical density divided by slope. Directly you will get the value of glucose concentration. This is how the standard graph of glucose is prepared. You can see at the concentration 0, you can see the color is yellow. Glucose concentration 2 millimolars, and you can see as the concentration increases, the color intensity it also increases, which follows the Beer and Lambert's law.